All right, we are back with part two. Part one, we talked about kind of the outline of what we wanted inside of this amplifier. I went back and cleaned up some of these text boxes with my iPad. I forgot I could hook up my iPad and work on all of this, but I quickly wrote down the first step is gonna be it's called a full wave rectifier. Essentially, we take in the AC signal, from the wall and it will convert it into a DC wave. So if you kind of want to know what that looks like, we start with a sine wave and it goes up to about 110 volts. Um, from there, what happens is we put it through these diodes. So what the diodes will do is with a full wave, it will conduct both waves. That's why it's called a full wave. You have a half wave and a full wave. The half wave will look like this. We'll start like this. It'll cut out. So this is the difference between a half wave and this would be a full wave rectifier. We kind of line them up next to each other. So this would be a full wave. And you can see the half wave is only 50% efficient. And this is closer to, like 80% or whatnot. We get more power. Specifically on the half wave, you'll have these long periods of no power, which will cause issues. But if we then add a capacitor to this, so we add in a capacitor like this guy. Now this will look something like this. Something like this, where this is all RC constant time values. We go to this guy, it probably looks more like this. So you can see clearly that the full wave rectifier is a little bit better. And of course I'm drawing this a little bit imperfect, but you can see that you want the full wave, so this is what I'll be doing. And that is after the cap, so that's what this capacitor does. Some notes that I put down here is that we're using 60 hertz, I believe, on the wall outlets. So we want something that will cover this time period. This is going to be the distance between the waves. So usually, if you want a longer time, you do a longer or larger capacitor value. I might actually do a staggered series of them or parallel series of them. So I might actually go through and put in some extra caps. So mine might actually look like this, where we have multiple caps. The benefit of adding the additional caps is it will filter the power a little bit better. The small capacitors will give the instantaneous power draw that it needs, and the large capacitors will have a larger store. And that should get rid of a lot of the signal noise that you would get from other noisy things on your power. So that might be your AC, your refrigerator, hair dryer, that kind of thing. Things that were going to draw a lot of power and create ripples. Hopefully the multiple caps will reduce that impact drought. And then the last step is a voltage regulator. The voltage regulator, I believe I'm going to do some sort of Zener diode. It's been a minute since I've used any Zener diodes, but essentially you'll hook up the Zener diode. You can model it with a resistor as well, because all this is essentially a resistor in the small signal analysis. So it's a resistor with a power supply. So this is how you model them. Essentially, what I'm going to want to do there is my goal is to keep that voltage at a stable level. So I want it to be about 100 volts. So I probably make this a 100 volt drop. So I'm going to assume that this is 100 volts and this is 0 volts. And I'm going to want that voltage regulator to keep that going. So I'd have to spec this out. I'd have to have the right current, and voltage. So that's how I will spec out that part. And then obviously we're going to, in our load, we will put an op amp in between them, hopefully. I've yet to figure out what I want to do. This isn't necessarily just the, we haven't gotten to the audio portion of this, so there will be a need for a preamplifier circuit, which I might not use 100 volts for. I might have to step it down to 50 volts or 20 volts. 100 volts is a lot for an op amp. Not a lot of them actually use 100 volts. I was looking, there is an op amp that produces 100 volts, but it won't actually take 100 volts for the rail, so there might be a need to step this down in the future, so we'll find that out when I get into this part selection. Another thing that I should mention is that from my textbook that I am using to reference some of this material, that would be the Cedra Smith microelectronics circuit. I'll write this down real quick for you. So I'm using circuit. It's going to be the 8th edition. So this is the book that I'm referencing. I use this in my electronic materials classes. So I already have it on hand, and it covers some of these items. And this is kind of where I learned about some of these to begin with. So this will probably be the step 1. I want this to be separate. So this is the first detachable DC converter. So this is where this is coming from. So I'd like this right here to be this portion. I don't think that we need a ground in here. I know the ground is in case you short items, and then this will help you stay safe. I'm not necessarily sure what to do with this. I'm going to have to do a little bit more research. If anybody has anything, please let me know in the comments. I know that this ground level will be in the bottom here. These 110 and 1 neutral are obviously going to get hooked up onto the circuit right here. I'm going to use a DC power plug on this PCB supply. I have to make sure that the traces are big enough that they won't get cooked. The goal is maybe might need to draw about 3 amps, so I'll spec it maybe for 4 amps. Try to keep that nice and over-engineered. Same with the reverse voltage on these diodes. I'm gonna have to pick diodes that can have a reverse tolerance of 160 volts rather than 100 volts. And I think the caps don't really matter too much. I'll probably use electrolytic caps, and I'll probably put 3 or 4 of them, just like I said, so they can keep it cleaned and all put together. But that will be step 1 in turning the wall power into usable power for the DC amp.